Welcome to the second session of this short cycle of lectures. Now I will introduce Bayesian networks based on this brief introduction to brief review of statistics and introduction to probabilistic inference. Bayesian networks. It's the second, as I said, session in the series. What I will do now is introducing Bayesian networks and inference in Bayesian networks. I will also tell you about an extended family of graphical models, which Bayesian networks are a member of. The things that I hope you will get out of this session is knowledge, how to express probabilistic knowledge by means of Bayesian networks, understand how they perform inference, and also understand the relationship between probability and causality. That actually may be better to done in well, it's an introduction to our third session. Bayesian graphical models. That's the first topic. Just a matter of clarification. We are dealing with systems that are pieces of the real world that can be reasonably studied in separation from the rest of the world. And we have models, which are abstractions of systems used in science and everyday thinking. I put the word subjective here because they are subjective. Of course, as subjective as science is, it's something that a scientist will construct to model the world. Bayesian networks are, of course, models, not systems. Representation of probabilistic knowledge, a probabilistic model, it's always representation of the joint probability distribution over its variables. Once you have the joint distribution, you know everything that you ever wanted to know about the variables, how they interact with one another. So anything that you can do, that you want to do, you should be able to do with the joint probability distribution. Fundamental thing. Here is a representation of the joint probability distribution of the example that I gave you in the previous session. We have a disease. It can be present or absent. So you have a tree in which a circle represents a random variable and branches represent its outcomes. And we have two variables. When you have a second variable, you essentially add it to every branch of the previous part of the tree. A test can be positive and negative. And then representation of the joint distribution essentially is a measure over all combinations of variables, in discrete case, of course. So we have here all combinations of our two variables. They are binary, so there are 4 combinations. And you assign a number to each of the combinations. And that is essentially a joint probability distribution. It tells you how likely different combinations of those variables are. This is a very simple representation. In the past, in 18th and 19th century, books did not have too many illustrations. I guess it was the technology that was limiting. Today, we can do it much easier. They were not drawing those trees. Who knows actually what they were doing maybe when they were giving lectures. But many books will not have that. But when you read those early writings of people working on probabilities, you will notice that they were actually talking about constructs like trees, where joint distribution is essentially a measure put on all of the combinations of variables. Once you have the joint distribution like this, you can use it to perform useful calculations. For example, if you want to ask the question, what is the probability of the disease present? The way you would do it in this representation is you would add up those two, because these two are compatible with the event, the disease is present, and you would divide it by the sum of all, but the sum of all probabilities is 1. So just adding that. And that gives us 1 in 1,000, which is precisely what was the prior probability over the disease. A more complex question would be the one that we asked in the example. If you have a positive test result, how do you calculate that? Well, a positive test result makes the branches with negative test result impossible. They are essentially impossible. They are not consistent with what we know about the world. Then the only thing that remains is to look at the remaining events, combinations of events. There are 2 of them. We'll be normalizing by the sum of them. And in the and we take those branches that are compatible with the event of the disease present. That's the only branch, 0.00098 divided by the sum in order to renormalize the probabilities. And this expression gives us precisely what Bayes' theorem gave us, the probability of the disease given the positive test result. Of course, we would not do things like that. In fact, we would probably not even represent our joint distributions this way, but I just wanted to show you the basic idea that if you have a joint distribution, you can calculate anything from that. What is wrong with probability trees? The thing that is wrong is that, as you know, as you add another variable, the tree will grow exponentially. And that is not a joke, because if you have 10 variables, the number of branches, so the number of parameters that you will need, if they are all binary, is going to be 2 to the power of 10, which is 1024. You add just one more variable, and suddenly you need 11. You have 11 variables. You need 2048 parameters. When you have 20 variables, you need 1,000,000 parameters. 21, 2 million, right? So it's growing impossibly. Getting these parameters from an expert is impossible. Getting them from data is going to be also very hard, because in order to make these parameters reasonably reliable, you would need at least 10 times as many records. So 10 million records, and probably many more, because the records, the representations are not symmetric. So you would need a lot of data. In other words, this representation is useful for very small problems, but is quite impossible. And until at least the 1970s, maybe 1980s, people in artificial intelligence thought that using probabilistic inference methods is just impossible, because you would need too many parameters. You would kill yourself trying to represent those models. Luckily, there was an ingenious idea, really great idea, brilliant, that is by now only 40 years old or so. The idea was use independencies among variables in the joint distribution to reduce the number of parameters. The idea comes from 2 brilliant scientists. Philip David, he is a British statistician. In 1970s, he developed a theory of using independencies in representation of joint probability distributions. Yuda Pearl, who is a computer scientist, in 1980s, inspired by this work, by these ideas, developed graphical representations of joint probability distributions, what we know today as Bayesian networks. In any case, the two, the original ideas, and then bringing them to computer science and embedding them into graphical models, was absolutely fantastic, brilliant. Brilliant ideas are obvious once you have them. Of course, when you know this, it's an obvious thing to use independencies. My favorite example of brilliant ideas that are obvious is a wheel. We sometimes make fun of other people saying, oh, he rediscovered the wheel. What we mean by that is the wheel is such an obvious thing that rediscovering it is not a contribution at all. It's obvious, but it's also brilliant. And only when we have it, we find it obvious. But before you have it, it's not obvious at all. The proof for that is American civilizations. None of the American civilizations had the wheel. And Incas, you might say, they were running in the mountains. Maybe a wheel wouldn't be terribly useful, even though they did have hills and roads also. Aztecs, Olmecs, hills. But here is a couple of pictures that I took in Yucatan. Mayas were building roads, and they were using the roads just to walk on them. A wheel would make their life much, much easier. Apparently, they didn't have it. So it wasn't as obvious as we think. Once we have it, it's obvious. So the idea of representing independences is obvious, but it's still brilliant. How is it used? Well, here is the idea. You can represent any joint distribution as a product of distributions. That's a very easy thing, really, to do. It's the definition of the conditional probability distribution. If you look at, let's say, these two last elements, that's you have conditional probability of xn minus 1 conditioned on n times xn. Together, that is the joint distribution of xn minus 1 and xn. You do it recursively, and you see why you can do this. Essentially, you take first variable conditioned on the remaining ones, and you need to multiply it by the joint distribution over the remaining ones. You decompose it again and again and again and again until there's nothing to be decomposed, because the only variable that is left is xn. So factorization, or decomposing a distribution, joint distribution, into a product, that's an easy thing to do, quite easy to understand and obvious. We always keep one variable before the conditioning bar. If we do that, depending on the order in which we take those variables, we will have many ways of doing this. In fact, there is n factorial ways. If you have 4 variables, there is 4 factorial, which is 24 different ways of writing this. Now, some of these are more useful than others, because suppose you know about independencies in this domain. You know these 3 independencies, A independent of C. An example of knowledge that we have, we know that sex and intelligence are independent of one another. Women and men are pretty much the same IQ. There is some doubt about the spread. There is a different standard deviation, apparently, but they are independent in terms of the mean. Here's another example. There is a strong dependence between shoe size and reading ability. I don't know if you knew that. So people who have longer feet can read much better. But that dependence disappears when you condition on age. So when you look at 1-year-old people, 2-year-old, 3-year-old, 4, 5, 6, 7, 8, 9, when you look at the people in a given age group, then you notice that the shoe size and reading ability become independent. That's conditional independence. So once we condition on something, there is independence. And this is something we know. Of course, this is kind of, the example is, well, it's a real dependence and independence, but of course it's a joke. Children, essentially, the bigger the child, the older the child, the better the child can read, and the larger the foot is, right? But if you condition on the age, the dependence between the foot size shoe size and reading ability disappears. So suppose we have a set of independencies like this. Independencies can come from our knowledge, but they also can come from data. If you have a data set, you can test for independence, and there are statistical independence tests. Suppose you know these two independencies, then you can simplify the factorizations. And some of the factorizations are much easier to simplify than others, given our knowledge of independence. This one is in particular allows us to enter all three independencies. A independent of C. Probability of A given C is equal to the probability of A. That's the intuitive definition of independence. C tells me nothing about A. So I can replace this by that, probability of A, just by knowing that A and C are independent. D and A are independent given C. Look at this. D conditional on A and C. Once I condition on C, A is no longer needed here because probability of D is going to be the same as probability of D given A and C, of course. So we simplify this with that. And the same for the third independence right here. So we get a simpler factorization. Now, what are Bayesian networks? Bayesian networks are graphical representations of these factorizations. If you have a joint distribution between among A, B, C, D variables, if you have a factorization like this, then you can draw a graph. You draw an arc from the variables behind the conditioning bar to the variable before the conditioning bar. A has three conditions, B, C, and D. Please note that A has three incoming arcs, B, C, and D. B will have two incoming arcs, C and D. C and D come into B. C will have only one from D, and D will have no incoming arcs. So just the mechanic procedure of drawing a graph from the factorization. Every factorization will give you a Bayesian network. But some factorizations are more useful because you can simplify them. If we simplify this factorization by means of independencies, I showed you that on the previous slide, you get a simpler Bayesian network. You can observe one very important thing. This, by the way, is a theoretical view, very theoretical. In constructing Bayesian networks, we rarely use this view, but this is the theoretical foundation of Bayesian networks. The important thing that you will see here is that independencies lead to removal of conditioning variables. You saw what I did. I removed C from A. I removed A from here. So every independence results in removing a conditioning variable, which means removing an arc. The important thing is that absence of an arc is a graphical representation of independence. So that's it. That's Bayesian networks. And then you can all see kind of the representation, the graphical representation showing you independencies. In fact, the absence of the arcs is independence. There are three arcs missing in this graph. Missing means missing from a complete graph. There's no arc here, and no arc there. Three missing arcs. There are three independencies represented by this graph. The thing that I'd like you to point out is that in the product, in this factorization, we have either a priori distributions like A, probability of A, probability of C, or we have conditional distributions, D given C, D given C. So there will be here a conditional probability distribution encoded. And that's what Bayesian networks are doing. We'll play with that more. To sum up, the trees, which are easier to understand in the beginning for very small problems, are the same as Bayesian networks in terms of representing joint probability distributions. But Bayesian networks are much more efficient. Here is an example of a practical Bayesian network. This model contains 70 variables. If they were binary, and they have some of them have more than 2 states, they would have 2 to the power of 70 parameters that are needed. That's 10 to the power of 21. That's a huge number, really huge. With the independencies that you see here, please note that there are only 123 arcs. There are 2,400 missing arcs, independencies. With these independencies, we only need 2,100 parameters to represent the joint distribution among these variables. In case of this model, the model was constructed using not the theoretical mathematical approach, but was constructed using causality, causal connections. We'll talk more about this during this and also the next session when we talk about discovery. So I will tell you more about this. If you kind of blow up part of it, you'll notice that that the arcs can be given a causal meaning. For example, diabetes is a risk factor in obesity. And obesity is a risk factor for a disease known as hepatic steatosis. Hospitalization has causal impact on the history of transfusions, and that can be a risk factor to hepatitis. You can get a virus, hepatitis virus, from that. Surgery also influences the transfusion. So causal connections. We'll talk about this more, so please be patient about this. This is an impressive model. You can find it among the example models in Gini. It's a model that is constructed for diagnosis of diesel locomotives. It has a lot of arcs, 3,600 arcs. That's a lot. In fact, when you look at it closer, you see that it's a spaghetti of connections, a lot of connections. But it's not the arcs present that make it interesting. It's the arcs missing. It's missing over 2 million arcs because there are over 2 million independencies encoded in this model. And if you were to represent this by a tree, you would need 2 to the power of 2,100 parameters, and that's around 10 to the power of 600. To give you an idea of the size of this number is that currently scientists believe that the number of atoms in the observable universe is around 10 to the power of 82. So this number is a gazillion times the number of atoms in the observable universe. So you see the power of Bayesian networks. Suddenly, models that were completely out of the question can be represented with as few as 12,000 parameters. In this case, they were not terribly worried about this number because they had a lot of numerical data in fault trees constructed for the locomotives. So they got those numbers from fault trees. So here is the power. The Markov condition, something that you would be interested in. It's essentially an axiomatic condition that describes the relationship between the structure of the graph and probability. The Markov condition sounds as follows. A variable in a graph is probabilistically independent of its non-descendants given its immediate predecessors. With the Markov condition, you can look at the graph and you can say which things are independent and under what conditions. It's an assumption that ties directed graphs with probability. it specifies how directed graphs represent independence. We'll talk about a very closely related condition known as causal Markov condition. It's going to be more interesting to you, and we'll come back to that maybe later in this session and in the next session. Perhaps we can talk about the details and the intuition behind Markov condition at that point. Before we get there, though, let's look at an example. Here we have joint distribution over these 7 variables. Here is the joint distribution, and it's factorized, as you see. It's already including the independencies. Essentially, every node that has parents, it is represented as a conditional probability distribution, and nodes without parents as a priori distributions. This is a picture of a Bayesian network, of course. You see the display of marginal probability distribution. We talked about marginal during the previous session. So marginal distribution of wet grass is 24% wet, 76% dry, and etc. for all the others. This graph represents independencies. In fact, how many independencies? Well, exact number is going to be hard to calculate in my head, but roughly, how many arcs will this network have when it's a complete graph? We have seven nodes. How many pairs are there? Number of combinations of 7 over 2. And that's how many? 7 times 3. There should be 21 arcs, I think, in this graph. We have only 6 arcs, so 15 arcs are missing. There are 15 independencies encoded in this graph. And Markov condition tells us, we'll talk about this, maybe I should postpone this, to show you how Markov condition works in practice when we have a causal model. So let's postpone this, just a few minutes. In any case, this model represents quite a number of independencies. There should be 15 independencies represented by this graph. The Markov condition essentially says that a node is independent of the rest of the network, given its parents, and so a node is independent of its non-descendants, given its parents, right? So let's take healthy grass. It's independent of everything that is non-descendant. There are no descendants, given its parents. So if we condition on wet grass and fertilizer, that will screen off healthy grass from the rest of the network. But again, please just wait. We will spend at least 20-25 minutes on this, playing with practical examples. A Bayesian network is another view of it, so non-theoretical, is essentially that we are dealing with the structure, which is typically a causal graph. We try to draw causal graphs showing influences among the variables, and the quantitative part, which is essentially the probability distributions over these variables. If we go there to the distributions, you can imagine them as tables inside those nodes. If there are no parents, there is a priori marginal distribution over this variable. If there are parents, then you have distributions that are conditional on the parents. There's one parent of this node, age. We have conditional probability distribution over age. For every possible value of the age, we have a distribution. If you have multiple parents, then you have combinations of parents. For every combination of states of parents, you have a conditional probability distribution. Absence of arcs, so arcs that are missing, lead to reduction of the size of the table. And that's how the reduction of the parameters that you saw in the 2 big examples. What can we do with Bayesian networks? Everything that we can do with joint probability distributions. So you can answer the question, for example, what is the probability of invasive cervical cancer? That's one of the states of this node. In a patient with high-grade dysplasia, that's one of the results of a pap test, one of the states of this variable, and history of HPV infection. Cervical cancer is a venereal disease, pretty much. It's caused by a virus spread during sexual intercourse, typically during sexual intercourse. So it's a causal factor, HPV infection of cervical cancer. Age is just changed with, after the infection, you need to live a little bit longer to develop cancer, of course. That's why the age. And this is one of the tests for cancer and the HPV. The HPV infection impacts the result. So we have two observations, and we can imagine those two observations spreading around, spreading in the network, the rest of the network. That spreading, you can imagine that as application of Bayes' theorem. Essentially, observation allows you to calculate the posterior distribution in the neighboring nodes and spread this way throughout the network. It's more complex than that, but we will not be getting into the algorithms for Bayesian networks. Theoretically, answering this question is essentially calculating a conditional probability distribution, which is easily derived from the joint distribution. It is theoretically easy. The more sparse the network, so the more independencies there are, the faster the inference. So that also helps, not only with representation, but also with the speed of inference. There's another thing that you can do with Bayesian networks that fewer people will talk about, but still they do. Yuda Pearl, his work on causality absolutely talks a lot about this, and scientists talk about this. Changes in structure. When you manipulate with something, external manipulation, these things have been done for the last 100 years at least. Econometricians were building econometric models which were predicting the effects of manipulation of systems. Suppose you decide to vaccinate the population. So essentially you impact this variable, you manipulate it. When you manipulate this variable perfectly, then the other incoming arcs become irrelevant. I'll talk more about this in the next session. And then you can predict what will happen if you vaccinate the population or if you vaccinate a patient. You can predict again the posterior probability distribution over that. You can do that only when your models are causal, when the meaning of the arcs is causal and corresponds to our, well, actually real causal structure in the world. Then you can predict successfully the effects of manipulation. One of the last things in this session, before we start playing with Markov condition, is that Bayesian networks, of course, it's a new, interesting formalism, but they are deeply rooted in things that we have already known before, and there are things that we can do with them easily. I will not talk about this much, but there are qualitative Bayesian networks where the number of parameters is much smaller, and the posteriors are shown by colors. Every node is a proposition, and probability is shown by the color. A green, generally probability 1, dark green, dark red, probability 0, and anything in between can be shown. You can also observe things, you can manipulate, and they recalculate the distributions over different variables. I mentioned to you that that econometricians were building causal models and making predictions of the effects of manipulation. Here's an example of a causal model that has this econometric flavor. It's a causal model. Causality was explicated here by one of my advisors, Herb Simon, in 1960s. he has explained why econometricians were able to make predictions. You can make predictions that are causal when the model captures causality, and it captures causality when each of these core equations is describing a unique mechanism acting in the system. And how do you know what a mechanism is? Well, because there are physical, social, chemical, engineering laws that you can capture, economic laws that you can capture by individual equations. For example, student-teacher ratio is number of students divided by the number of faculty. Class size is the number of students times number of hours per week that they take, divided by the number of faculty times the number of hours they have to teach. Faculty salary comes from two sources: tuition paid by students, so number of students times tuition, plus grants, other income. And you divide it by the number of faculty times 1 plus overhead. Overhead are additional expenses, paying non-teaching faculty, paying heating and light, etc., electricity. And the second thing that is required in econometrics is that the equations that are essentially set to values or to distributions, they are exogenous, truly exogenous in the system that you are modeling. So they are set on the outside. If you have that, Herb Simon has shown, sorry, it was 1950s, and that you can draw a directed graph that represents the flow of information and causality in this system. If you look at this graph, you'll notice that the exogenous variables have no incoming arcs, and the other variables are derived from those core equations. The flow of information. In order to solve this equation for student-teacher ratio, you need these two variables, and you see the arcs coming in. So a very interesting link between these systems and causality and Bayesian networks. Bayesian networks are in fact relatives, distant relatives of these systems. I'll show you the structural equations are more powerful, actually. You can do the prediction of manipulation. Suppose in this system that describes the money flow in a university, we decide to manipulate from the outside, intervene, and set the student-teacher ratio to 10. You need to let go one of the 10 equations, because otherwise you would have 11 equations with 10 variables, over-constrained system. So you need to let something go. Suppose we decide to let this go, which is the number of faculty. So essentially, the university is saying, if needed, we'll hire more faculty, but we want to set the student-teacher ratio to 10. If you do that, you can derive a new ordering, causal ordering, and this is the new graph corresponding to this new system of equations. It's a more powerful operation than plainly arc cutting that you saw in Bayesian networks. But again, we will not talk much about this. I'm just showing you the family of systems that are relatives of Bayesian networks. General equations and graphs, it's really very, very close, very similar. The directed graphs, you can derive them from the equations, and you can also derive them as Bayesian networks. Spreadsheet models, in fact, you can view them as systems of equations where a cell can be defined by an equation. If you draw an arc from the cell that is feeding another cell, you will get a graph, a directed graph. Of course, it will become a spaghetti, so not a terribly good interface, but they are very, very close. Directed graphs are a better interface. There's also a class of programs, software tools that are known as visual spreadsheets. Not everybody uses the term visual spreadsheets. In fact, my favorite program, Analytica, developed by my advisor, Max Henrion, they call it influence diagrams, which is not really too far from the truth, although some people would call it visual spreadsheets. They are also directed acyclic graphs that are modeling interactions among variables. This is really very close to Bayesian networks, not far, really. Here is a Bayesian network that is hybrid. It is modeling a system of equations, similar to what you saw for the university. We have these three, I think it's two equations, because it's either this or that, depending on when you are heating or cooling. And this equation, it's embedded in these two variables with parents. The parents are usually constants and distributions of values. It's hybrid because you can have both continuous, like here, and you can have discrete distributions. What you see is marginal probability distributions. Probability distribution can be marginal discrete, like here, or it can be continuous. You see plots, histograms displayed. I'll show that to you in the software. Directed graphs give you if they reflect the causal structure, they give you the insight into the problem. They can also accommodate representation of uncertainty. You can reconfigure them. They have good theoretical foundations, and you can really talk the same language with statisticians, philosophers, and scientists. In fact, people who do work on causal discovery are statisticians, computer scientists, but also philosophers. In fact, an important approach to causal discovery comes from a group in the Department of Philosophy at Carnegie Mellon. It's really the same language with statisticians, philosophers, and scientists. You can also have, and this is another relative of directed graphs, known as dynamic Bayesian networks. It's corresponding to systems of differential equations, in fact, difference equations, because time is discrete here. These graphs can be cyclic because in temporal sense, if you recall systems of differential equations, you can refer to variables that can be feedback. So variables can influence themselves over time. So this is what is shown here. I wasn't planning to talk about this today, but I just wanted to make you aware that this can be done. Graphs were drawn for systems of differential equations by Iwasaki and Simon in early 1990s. You can derive probability distributions over time, how they change over time. Yes. You can extend Bayesian networks, which are models of the world, into influence diagrams. Influence diagrams are representations of decisions. So in addition to the model of the world, you have also a model of interventions, of things that you can do. So these are almost like variables in the world, but they are under your total control. You can decide what the values are going to be. And this part are utility functions, essentially measuring the value of the different states of the world. As you intervene, you may influence the world, and that the new states of the world, they will give you new values. So solving influence diagrams essentially is optimizing, picking a combination of decisions such that will give you the highest possible value in your decision problem. Finally, something that we'll talk about in the third session is learning data mining. This part is easy. If you have data and a graph, you can easily learn the distributions. That's a matter of counting. If you have no parents, you just count the states in a single column. If you have conditional distributions, you look at subsets of your records, ones that are corresponding to the condition, and then again, you count how many times each occurred. That's kind of roughly, very informally, what learning amounts to. And then we can do magic. The thing that I'm going to talk about in the next session is deriving the structure from the data directly. Gini, I'm going to use it a lot, and the nice thing for academics is that our tradition, which comes from the University of Pittsburgh, is that we have made Gini available to the world of academia. It's free, you can just download and use it to do anything with Bayesian networks and graphical models. And Gini has quite a lot of powerful functionalities that I'm not going to talk about in this series of lectures, but I'm just going to show you the learning, but there are many other things. The architecture of Gini, if you decide to use these methodologies in your own programs, you can easily use the reasoning engine, the API, which is originally written in, well, actually not originally, it's written in C++, very, very fast. I would say maybe the fastest Bayesian network engine in the world. We have some evidence to show for that. Then we have a series of wrappers that allow it to be accessed from several programming languages. And something that you will see in these lectures is the API, is the GUI, it's the Gini. Everything that Gini does, it's really a stupid interface that translates every mouse click, every mouse stroke, whatever, to calls to smile. And there are some modules. We will look at learning and discovery module. There are others like diagnosis, qualitative interface, etc. The rest is with the software. Let me show you a little bit in this session, and then we will continue in the next session with learning, where there will be more use of Gini. Let me just show you first the Bayesian networks, a couple of Bayesian networks. Gini has this nice thing that you can access our model repository, online repository, directly from Gini. So we can download models from there. Let me load a very, very simple model, here's a good model. You can show any model as a graph with ovals. That's what Bayesian network representation typically is, but you can also show it as bar charts, where bar charts will show you the marginal probability of every node. Now we have marginal probabilities of every variable here. And as you observe evidence, you can observe it in several ways, but the easiest is double-clicking on a state. I'm double-clicking on this, and this, and this, and this. And what you see is that the probability, the marginal probabilities of some of the other nodes are changing. Essentially, the Bayesian network is recalculating the probabilities. Okay. Observe, unobserved variables. Because we have a joint distribution, we can look at things like strength of influences. We can calculate them. We can show by the thickness of the arcs, and also we can also, I think, show the sign of that influence by the color. What can we do? What else can we do? Let me show you another model that you saw on the slides. Here is a diagnostic model for diagnosis of liver disorders. The rectangles are shown. These are the possible diseases, the blue nodes. It's just something that the color you can assign to nodes, not part of the theory. These are the risk factors, and the green nodes are test results and symptoms. You can observe things like you can observe jaundice. I'm setting evidence to be present. Please note that some probabilities have changed among the diseases. Then there's also support for diagnosis. You can calculate the most informative observations from the point of view of this disease. Something as simple as the biological sex can tell you a lot about this disease. These things are worthless to ask questions about. You have experience, probably all of you have experience with calling a call center to help you with some problem with your computer, with your TV or whatever. They ask often useless questions. Because we have a joint probability distribution, we can calculate which questions are going to be most useful in the sense of giving us the most information about the disease here in red. So these are the most useful questions to ask. You see, as I get the answer, I'm almost certain that this is the disease. Let me clear all of this. I can also do differential diagnosis. So I can say, I want to know which of these 4 diseases is happening in this patient. Here are the most informative questions. These questions are, they did tell me something, but not a lot. But if I have something here, it shoots them apart immediately. With one question, actually, I pretty much made the 3 of the 4 very unlikely and the 1 very likely. What else can you do? So these are Bayesian networks. Let me show you the hybrid net, 2 more networks to show you. The hybrid network, the same idea. We have essentially Bayesian networks, but they are continuous. So if I look at this, for example, and look at the definition is an equation. You can use any functions that are here, any probability distributions, in order to define how this variable interacts with the parents. So it's almost like a system of equations. When you update, you get marginal distributions, again, of every node. Joint distribution is done by the whole network. If I start observing, it recalculates. A technical issue, when you observe something that has parents, unfortunately, the stochastic sampling no longer works. So what we do is we discretize the network on demand. You can define the discretization. Now, anything that you do is, in fact, like in a Bayesian network. I observe something, I observe value of 10, I see how things change. So it's a Bayesian network. One more thing, let me show a large network that I showed earlier. The machine diagnosis. You see, it takes a couple of seconds to load from the repository. Here it is. I showed it to you on the screen. I'm moving the mouse wheel so to make it larger or smaller. So you see, it's a spaghetti. Calculating it calculates only the faults in the machine. It takes a fraction of a second. Update, click, done. So inference, representation and inference can be very, very fast. Okay, anything else that I wanted to show you? I guess that's it. I don't want to get into this too far. We will talk about learning. In fact, large part of the learning is going to be, before we get into learning, we will play with causality. I'll show you the practical implications of the Markov condition in the next session.